Okay, so it's our great pleasure today to have Mateusz Wasilewski from the Institute of Mathematics of the Polish Academy of Science. So he is an assistant professor at this institute. He's interested in quantum graph, quantum groups, von Neumann algebra, and harmonic analysis. Please, you can start.
Okay, Sebastian, thank you very much for the invitation, for the introduction. So today I will talk about recent joint work with Mike Brannan, Daniel Gramada, Junichiro Matsuda, and Adam Skalski. So if you become more interested in this work after my talk, then the preprint is already on archive, so you can read the whole paper. So it's about non-quantity for quantum analog of Frucht's theorem from classical finite group theory, basically. So I will start with that, and then I will tell you what we want to do in the quantum setting, what can be done, what cannot be done, and things like that. So what is Frucht's theorem? So this is basically like a slightly more precise version of Cayley's theorem, right? Cayley's theorem says that for any finite group, any finite group is a subgroup of a permutation group. So I mean, any finite group acts on some finite set. And Frucht's theorem says that we can choose the finite set somehow and add a graph structure on it such that this group becomes precisely the automorphism group of the graph, right? So for any finite group, you can construct a finite graph, and the automorphism group of this graph will be the original group G. And how does one prove that? Well, I will discuss it in the next slide, and I will tell you what is the first non-quantitative generalization that one can hope for is, well, there are these things called quantum automorphism groups of graphs. So maybe all finite quantum groups are like that, right? So maybe for any finite quantum group, you can construct a graph such that the quantum automorphism group of a graph is this finite quantum group. But Banica and McCarthy studied this problem, and they actually produced many examples, and some of them really sort of easy, like very basic examples, really non-exotic, that cannot appear as quantum automorphism groups of classical graphs. So the way to bypass this issue is to also replace the graphs by quantum graphs. By this way, we have somehow more to act on, and this family of quantum graphs is sufficient for this purpose. So this is the main goal of this talk today. Okay, so let me maybe try to briefly describe how one proves this classical Frucht theorem, because the proof in the non-quantitative setting is definitely inspired by this. So first, what you do is that you have your finite group. It has some number of vertices, and you look at the complete graph on this many vertices. So if you look at the automorphisms of this graph, this is the full permutation group. So this is basically the way you prove Cayley's theorem. Okay, but now we use the group structure to somehow label the edges of this graph. So any edge in this graph is a pair of group elements, right? G, H, and then this H you can write as S times G for a unique S, right? Because we're in a group. And then we say that in this graph, such an edge will have color S, right? So we have as many colors as we have the elements of the group. And then if you look at the automorphisms of this graph that preserve colors, then they have to come from right multiplication. And why is that? I mean, because basically the edges GSG and like ES have the same color. So somehow, yeah, if you map the unit to some element H, then you have to map any element G to GH, right? Because of this basically group invariance, once you know what's the image of the unit, you know what are the images under this automorphism of all the other elements. So all of them have to come from right multiplication by some element. So it means that if you look at the automorphisms of this graph that preserve colors, you precisely get the original group G. But now you have a colored graph, so you need to find a procedure of constructing a classical graph from this colored graph. And this is somehow the main point of Frucht theorem. So the idea is that for each given color, you choose some specific graph. It's like a path of a given length, and then at one element of this path, you put somehow perpendicularly other path of different length for each color. Which is one of the choices. There are many choices that work here, but the idea is that you replace each colored edge by some fixed graph, right? So instead of the edge, you insert a subgraph there. And then for the same colors, you insert the same subgraph. For different colors, you have different subgraphs. And they are chosen in such a way that if you look at the automorphisms, they somehow have to preserve these subgraphs. And then it means that they come from these right multiplications. So by the way, whenever something is not clear, please interrupt me and ask questions and things like that. But I mean, I'm on purpose not going into the details here, right? This is just to give you a general idea of the proof, is that you first do this colored graph, for which it is easy to prove that the automorphism group is what you want. And then you perform some sort of decoloring procedure by making out of a color graph a bigger graph where you lose the colors. And we'll have the same scheme in the non-commutative setting. Okay, so I want to talk about quantum graphs. Today we'll talk about quantum graphs. So today, for the purpose of this talk, everything will be tracial and finite. So to have this thing, we'll start with this pair of a finite dimensional system algebra, right? So just a direct sum of matrix algebras, equipped with a trace, such that when you take the multiplication map, so M will be a map from B tensor B to B, then M star will be its Hermitian adjoint with respect to the GNS inner product induced by this trace tau. So it will go from B to B tensor B. Then the composition MM star goes from B to B, and we want this to be the identity. So there is a unique trace, like a unique tracial functional, positive tracial functional on B doing that. So if B was a single matrix algebra, right, Mn, then this trace would be n times the usual trace, right? So this may be a non-standard normalization, but it depends on where you come from. Like if you come from subfactors, this is, I think, the normalization for the Markov trace or things like that. So this is fairly natural normalization. And with this normalization, it has this nice feature that the value of tau at 1 is exactly the dimension of the algebra B. Right? So we think of it as the analog of the counting measure on a finite set. Right? So somehow instead of working with the uniform measure, we rather work with the counting measure, right? Which is not a probability measure, but the formulas get nicer. And also this is a thing that you can generalize to infinite direct sums. And the uniform measure you cannot do. And the main example today will be the algebra of functions on a finite quantum group. And then the functional will be the Haar measure on this finite quantum group. So if we have such a pair, then there are basically 3 ways to define quantum graphs. So classically, a quantum graph is, it's a relation on a set, right? 2 vertices are related if there is an edge between them. So a relation, it's just a subset of the Cartesian square. Cartesian products in operator algebras correspond to tensor products. And then, a subset is just the same as the characteristic function of the subset as a function, which is a 0-1 valued function, which should be a projection in operator algebra. So basically, a naive definition would be to start with a projection in B tensor B. But for technical reasons, it's better to work with B tensor B op, where B op is the opposite sister algebra. And then from this projection, you can construct two things. So you can construct a map from B to B, which I will discuss briefly later. But this is basically, if you know from quantum information the correspondence between completely positive maps and the Choi matrix, this is exactly it. And on the other hand, whenever B is represented on some B of H, then using this projection in B tensor B op, well, it has two legs, right? One is B, yeah, the other is B op. So the leg coming from B will act from the left. The leg coming from the right, B op will multiply from the right. So this will be an idempotent mapping on B of H. So the image will be some subspace V. And because we multiply by things from B and B op, this image will be invariant under multiplication by the commutant. So that's how we'll get B prime bimodules. Now I want to maybe quickly discuss how, a bit more precisely how you go between these definitions. So the first definition, maybe a bit more precise, is B is a von Neumann algebra. In our case, today, finite dimensional, sitting inside some B of H. And a quantum relation, this is a definition due to Weaver, is a weak star closed B prime bimodule V inside B of H. So it might seem like a maybe very abstract definition, but we'll see how it relates to some of these more naive ones. So a nice thing is that in principle, we choose a representation here, but if you choose a different representation, then you can relate quantum relations in one representation to quantum relations in the other representation. So basically, theory is independent of the representation, and there is also a way to just write it in a representation-free way. But I think for the purpose of this talk, it's definitely convenient to have this representation. Okay, so I basically told you already how to do it, right? If you have a projection in B tensor B op, and B is inside B of H, so it's a subalgebra. So of course, elements of B act on B of H, and then the first leg, as I said, acts as the left multiplication, the right leg acts as the right multiplication, and the image will be a B prime bimodule. So the thing that is maybe slightly more interesting is how you go back. Yeah, and I also mentioned the names here, Duan, Severini, and Winter. So they introduced quantum graphs as operator systems, but they only did it in the case where B is Mn sitting inside Mn, so H is also Cn. So this is this minimal representation. Then the commutant is just the scalars, so they didn't have this. They didn't have this extra condition of being a bimodule. I mean, a bimodule over the scalars, which is just a vector space. Okay, and then they talked about operator systems, which I will try to convince you at some point that operator systems, so subspaces closed under the adjoint, correspond to undirected graphs. Right? So here we have general quantum relations, and then the symmetry condition that you are closed under the star will correspond to the quantum graphs being undirected. Now I want to discuss briefly how you go from the bimodules to projections. I mean, basically, I think you can imagine what's happening. You have this bimodule, so you want to write some sort of orthogonal projection onto the bimodule, which will be a bimodular map, and then all B prime bimodular maps are represented by elements in B tensor B op. This is basically the procedure, but you need some sort of inner product to define these orthogonal projections. So for this, we can use this procedure that Hagerup described, I mean, in much greater generality, is that so the generality that Hagerup had was that you have an inclusion of phonemic algebras n inside M, and you have an operator valued weight from M to N. Then to this you can assign the inverse of this weight, which goes from the commutant of N to commutant of M, right? So if you have a map between phonemic algebras, somehow a nice operator valued weight, then you get a similar type of a map between the commutants. So in our case, we start with tau, which is the functional, so it goes from B to C. So C is just a scalar, so the commutant is everything, right? It's B of H, and this map goes into B prime. And what is nice is that this equality that we assume that MM star is identity, so I said that this is the analog of a counting measure, that this precisely corresponds to the fact that this inverse of tau is a conditional expectation, not merely an operator value weight, but an actual an honest to God conditional expectation.
Then, as I said, why it is called inverse? In what sense it is an inverse?
Yeah, I'm not sure. I'm not even sure if it is called that. I think it's written like that. I'm not sure.
Oh.
Yeah, I'm not sure why it's called an inverse. Yeah, it's a procedure. I mean, yeah, if you do it twice, you get to the original one. But yeah, I'm not sure why precisely inverse. Yeah, you need some terminology for that. But yeah. Okay, and then for the simplest case, right, where B is just a single matrix algebra and tau is this suitably normalized trace, then tau inverse is just the normalized trace. And then if you have a direct...
Will it also be faithful?
Sorry?
The conditional expectation, will it also be faithful if you start with a faithful function?
Yeah, it will be faithful, yes. Yeah, correct. And then you can, in this case that we are working here today, right, with where B is a direct sum of matrix algebras, you can explicitly write down the formula basically, because you know what's the formula for a man. Any representation of a man is, just the standard representation. I mean, the usual representation tensor some auxiliary Hilbert space. So you just somehow slice with respect to this normalized trace on your representation. And then for direct sums, you just decompose this somehow into direct sums and you get a formula as well. So this is, in this very simple setup that we have here, it's very explicit. Okay, but what is nice is that if you have this conditional expectation onto B prime, it means that the subspace of H will be equipped with a B prime valued inner product. And of course, if we are finite dimensional, then automatically this will give you a Hilbert B prime module. In general, it will be like a pre-Hilbert B prime module, not necessarily complete, but in our finite dimensional setting, it will be complete, right? And then also, since everything is finite dimensional, then Hilbert modules have orthonormal bases and they admit orthogonal projections. So there is a map like that. So there is an orthogonal projection onto this bimodule V always, which is a B prime bimodular map. And then using another theorem of Hagerup, such a B prime bimodular map is represented by an element in B tensor B. So this is how you go from bimodules to projections, right? Roughly, you want to write an orthogonal projection onto the bimodule and then represent this as an element in B tensor B. So this is somehow explaining one of these correspondences, right? Going between bimodules and projections in B tensor B. Now we want to go from this projection in B tensor B to
I want to ask one thing. So that tau inverse was basically the orthogonal projection onto the set of all quantum relations, right? This P tilde thing is your tau inverse, right? And in the context of direct sum of matrix algebras and all?
No. So this is the thing is that using tau inverse, you can define an inner product, and then there is a map, because I mean tau inverse always maps inside B prime, right? and this such a bimodule V doesn't have to be inside B prime.
Okay, sure.
Yeah, right. So you use this tau inverse, but it's not the same map, definitely.
Not the same map. Okay, fine.
Okay, and then want to write the. So maybe I want to make a comment here. I forgot. So when I was here, so as you see in the definition of a quantum relation due to Weaver, any sort of functional on B is not mentioned, right? This is just B is a fundamental algebra, and then you define quantum relation to be this thing. Right? So this is, and I mentioned in the previous slide that somehow to define quantum graphs, we really start with a pair of the algebra with a fixed functional satisfying external assumptions. So where it appears the functional is here, right? To have a nice correspondence between this definition via bimodules and these projections. This somehow only comes up here. And now in the other correspondence with the projections versus some nice maps on B, this will also use the inner product, right? So I was explicit here. Just on B, we consider the usual GNS inner product. Then there is a map between linear maps on B, right, and the morphisms of B to B tensor B op given like that. So if you have two elements, A and B in B, you can consider this rank one map, right, where you, when acting on some X, you take the inner product against B and then take A as an image, right? So this is the bracket notation that I quite like. And then you map these to the simple tensor A tensor B star op, right? So we use B star because the inner product is anti-linear in B, so we need B star for this to be a nice linear correspondence. Right, so this is basically, representing a linear map as a matrix, roughly. And then this procedure, this correspondence has many nice properties. So for example, if you multiply two Choi matrices of some linear maps S and T, and this is a Choi matrix of some sort of product of S and T, which is written like that, right? So we have this map M star, the adjoint of the multiplication, which goes from B to B tensor op. So then you take the tensor product of S and T, and then you multiply, right? So this is another map on B. So this will be a crucial property for us. Then we also have this nice thing that the Choi matrix is self-adjoint, right? So it's a element of B tensor B op, and this is a self-adjoint element, if and only if the original map will start preserving. There is basically, this is Choi's theorem, right? That's the matrix Choi T is positive if and only if T is a completely positive map. And then I wanted to relate also this thing to the symmetry that I mentioned, right? That's in the Duan, Severini, and Winter definition, they work with operator systems, right? So self-adjoint subspaces, and that should correspond to undirected graphs, right? So if you look at this projection in B tensor B op, thinking of it as a relation, right? So we have edges, then somehow taking the flip of the projection P is the same as reversing the edges. Okay, and then so the graph is undirected if this reversing the edges that doesn't change the relation. And this corresponds exactly to the map T being symmetric with respect to the GNS inner product. Okay. So here we have a definition of a quantum graph in this language is that we'll call a completely positive map A from B to B a quantum adjacency matrix if it's idempotent with respect to this different product, right? So this precisely corresponds to, using the first line, that the Choi matrix of A is an idempotent, and then since we assume that it's a completely positive map, then this idempotent will be positive, so it will be an orthogonal projection, exactly the thing that we started from, right? as this naive definition. So equivalently, because a projection is a positive operator if and only if it's an idempotent is a projection if and only if it's a positive operator, if and only if it's a self-adjoint operator. So here, equally well, if you prefer, you can assume that A is just a star-preserving map, which satisfies this extra condition, and then automatically it will be completely positive. Or maybe it's a better definition, because checking that something is star-preserving is much easier than checking that something is completely positive. Maybe, but I quite like, somehow I'm very used to working with completely positive maps, so that this is typically the definition I write. Right, so I wrote that these are called sure idempotents, because if you do this in the classical setting, right, so where B is a commutative system algebra, just Cn, then this product, this conjugation by M star of the tensor product is the sure product or sure Adamar product of matrices, right? So for matrices, we have the usual product, the composition of operators, but also you have this product that, when you enter the first year linear algebra course, this is the product you're not supposed to do, right? Which is just the entry-wise product of matrices. So this is precisely it. This is the sure Adamar product. And this formula, maybe if you work with the sure Adamar product, it should remind you of the thing that you can represent the sure Adamar product as a corner of the Kronecker product, so the tensor product of matrices. So this is exactly this formula that you take the tensor product and somehow using this map M star, you cut out a corner of this matrix. So this will be our working definition of a quantum adjacency matrix, and of course, a quantum graph will be this algebra with functional equipped with a quantum adjacency matrix. What is nice about this theory is somehow it's nice. You can pass between these different definitions, right? Because between quantum adjacency matrices, between these projections in B tensor BOP, and between these bimodules, and somehow each of these definitions has its merits. For example, the quantum adjacency matrix is nice somehow theoretically, like you can easily define symmetries in this setting and things like that, some invariants. But these bimodules are very nice for constructing examples, right? Because in the simplest case where you have just one matrix algebra, so the commutant is just the scalars, then you just look at subspaces of a man, right? And then these are very easy to construct. And then by going through these correspondences, you can also write down the formulas for the quantum adjacency matrix. I think this is something I already hinted at, that we'll call a quantum graph undirected if the quantum adjacency matrix is GNS symmetric, right? So assuming complete positivity, it means the same as being self-adjoint with respect to the GNS inner product. Now this is something that will also be useful later on, is that, and this is one of the invariants that is easy to introduce using the quantum adjacency matrix, is that the image of the unit will be called the degree matrix of the quantum graph. So classically, if you have a classical graph and an adjacency matrix, if you apply it to the unit in the algebra, which is the vector of all ones, then the image will be exactly a vector of degrees of vertices, right? So in the first spot, we'll have the degree of the first vertex, in the second spot, the degree of the second vertex, and so on. So here in quantum graphs, we don't have individual vertices so we don't have individual degrees, but we have this global object, the degree matrix, which is very useful. So this is somehow a nice sort of almost numerical invariant of a quantum graph. Okay, right, so this is basically, introduction to quantum graphs. So maybe do you have questions here before we move on to quantum groups?
It's okay, no question.
If not, sorry?
It's okay, you can go.
Okay. Okay, thank you. So we continue. So I assume that for this crowd, this is a seminar on quantum symmetries, so then I don't have to talk a lot about quantum groups. And today, all quantum groups will be finite, so also there will be no analytical difficulties. But I wanted to just recall the basic definitions, right? So a compact quantum group will be just, I forgot. So it should be a unital C-star algebra, which we denote as C of G, equipped with a co-associative star homomorphism from C of G to C of G tensor C of G. Right, so co-associative just mean, the dual condition to associativity of the group multiplication. And then in groups, you like having inverses, but then this analog of the inverse map for general compact quantum group is not that nicely behaved. So Voronovich had this very nice idea to replace it by the density conditions, basically saying that the image of delta times 1 tensor C of G is dense in C of G tensor C of G and other condition like that, which classically corresponds to this G admitting cancellation, right? So if you multiply by 2 elements and you get the same element, then somehow they have to be the same. And then you use the classical fact. So this delta corresponds to multiplication, right? So if you have this unital C-star algebra corresponds to somehow a compact space, then with a multiplication, so a semi-group, and then these density conditions correspond to cancellation laws. And then there is a nice classical fact that if you have a compact semi-group with a cancellation laws, is actually a group. This is how this definition works. So it seems very, very general, but it's somehow robust enough to allow nice theory. For example, you can prove within this theory that there's a unique Haar measure on a compact quantum group. There's nice representation theory, like the Peter-Weil theorem. So any representations, decompose into irreducibles. Irreducibles are finite dimensional and they have appropriate multiplicities. There's a left regular representation because you have the Haar measure, things like that. And then this is somehow at least for me, the main point of the theory of quantum groups is that they admit a generalization of the Poincare duality, right? So if you have a compact quantum group, you can construct a discrete dual. As the algebra function will be the direct sum of the matrix algebras corresponding to representations of G. Right, so alpha is a d alpha dimensional representation, and for each such alpha, you get a matrix block like that, and then you take the direct sum, and then using the left regular representation of G, which you can do, right, because you have the Haar measure, and you can define the so-called multiplicative unitary, and then using this multiplicative unitary, you can define the co-multiplication on this discrete dual. And as I mentioned, today we only deal with finite quantum groups, so this will always be just a finite direct sum. So there are no analyses. Okay, so as I mentioned in the proof of the Frucht theorem, basically you first start with this colored graph, right, which is like a Cayley graph of the original group with respect to all the group elements chosen as the generating set. So to perform this step, it's nice to work with analogs of Cayley graphs for quantum groups. And then what should be the quantum adjacency matrix for a Cayley graph? Classically for a Cayley graph, we have a generating set S, and then the quantum adjacency matrix is just a convolution against the characteristic function of this set. Or equivalently, if you have a Cayley graph, right? So edges are of the form G S G. It means that the group acts on the right on this Cayley graph. So then, if you have your adjacency matrix has to commute with the right action, and then this is a general fact that if you commute with the right action and in an operator, it means that you have to be a left convolution operator, right? So that your quantum adjacency matrix, if you want to somehow have this nice right action, which we do, will have to come from left convolution operators. And then we would like to check which of these can be quantum adjacency matrices, right? And there's this nice formula that if you are given two convolution operators, one against P1, the other against P2, then this Schur product of the two will be given by a convolution operator against the product. So from this, you can show that a convolution operator is a quantum adjacency matrix if and only if P is a projection. So maybe from what I wrote here, you need an idempotent, and then the star preserving condition will precisely correspond to P being self-adjoint. So the self-adjoint idempotent, which is an orthogonal projection. And then this is the symmetry condition, right? We might want to talk about undirected graphs. And then, so this quantum adjacency matrix is GNS symmetric if and only if P is invariant under the antipode, right? Which is the analog of the inverse of the quantum group. And since we're talking about finite quantum groups, there are no issues with this antipode, right? It's a well-defined object. So yeah, I already mentioned it. So for quantum Cayley graphs, right, you want to talk about generating sets. So the analog for a projection, in a function algebra of a finite quantum group to be generating means the following. So you look at this projection, you take higher and higher convolution powers. So classically, would correspond to looking at, the P corresponds to edges, then convolution square of P corresponds to paths of length 2, and so convolution of length n will be paths of length n. But in this convolution, you also count how many paths there are. So the convolution powers of P will not be projections. So we will look at the support projections, right? So classically, if you have a matrix, with positive entries, then you replace all non-negative entries by 1, basically, and then all the 0 entries remain 0, right? This is taking the support projection in this case. And you want the union of those, the supremum of those, to be everything, right? So you want to be, by taking longer and longer paths, you want to be able to cover the whole group. This is the idea here, right? So this is somehow connectedness of the Cayley graph. So this is how you can define the Cayley graph, right? You want the generating projection, you want it symmetric, right? So projection to be close under the antipode, and then this condition is the co-unit, so analog of the unit applied to P vanishes, means that your generating set somehow doesn't contain the identity. This is also a typical assumption for quantum Cayley, for Cayley graphs. And then such a pair, so you have this algebra with this convolution operator will be called a quantum Cayley graph of gamma. And then there's this nice thing, I will not go into the details, is that just like classically, if you choose two different generating sets, as graphs, the Cayley graphs can be very different, but somehow as metric spaces, they are isomorphic, so they are bi-Lipschitz equivalent. And you can define bi-Lipschitz equivalence for quantum metric spaces as well, and one can prove that two different generating projections satisfying extra conditions, the resulting quantum Cayley graphs, they also are bi-Lipschitz equivalent. So it is a nice somehow metric invariant of the discrete quantum group gamma. Okay, so now we have the preparation done. So we come back to the Frucht theorem, and I will discuss now a bit more details, for example, about these counterexamples of Banica and McCarthy and how we proved our main result. So yeah, I'm recalling that Frucht theorem says that every finite group appears as the automorphism group of some finite graph. And there is a second question. So that, as I said, the proof of Frucht theorem has two steps, right? First, you consider the Cayley graph, which has, as a colored graph, has the same symmetries has the original group as the symmetries. Then you decolor it. But it is possible that maybe you can choose a Cayley graph in such a way that you don't need a second step, that already the automorphisms of this Cayley graph are exactly the original group. And what his conjecture was that for a finite group, you can do this, well, unless some things happen. So, for example, like with G's, if G is abelian and all elements are of order 2, then, for example, taking the inverse, will be somehow will not be nice. Then G is generalized dicyclic, so this is also some other type of groups which are very close to being abelian. And then there are some finitely many exceptional examples. And unless you're one of these, then you can find a Cayley graph of G, which already has G as the automorphism group. So you don't have to do this second step, basically. And this conjecture has been proved. So it was a conjecture, but I mean, now it's a theorem by somehow many people contributed to it. So I want to discuss these two questions roughly, right? So the first one, to have just Frucht theorem, a very general statement, and then tell you maybe for which finite quantum groups we don't need this second step, so we can already find quantum Cayley graphs with the required symmetries. So maybe I wanted to mention that there are very easy examples that do not arise as quantum automorphism groups of graphs. And Banica and McCarthy, they prove, for example, that the dual of the permutation group S3, which is basically the smallest example you can have, already is not a quantum automorphism group of some classical graph. They have more examples. And then, of course, it's a very nice question now to understand which quantum groups can arise as quantum automorphism groups of classical graphs. I don't know how to solve this problem. I think it's very interesting, and probably very difficult as well. But you can somehow bypass this issue by working with quantum graphs instead of classical graphs, and this is what we proved. Whatever finite quantum group you start with, you can construct a finite quantum graph such that this finite quantum group is the quantum automorphism group of this quantum graph. So yeah, I want to maybe discuss briefly how we prove it. So first of all, you need to prove the colored version. So gamma will be a finite quantum group. So L infinity of gamma, it's a finite dimensional system algebra. So there are some projections generating it for sure. I mean, it has plenty of projections, right? And then for each of such projections, we consider the quantum adjacency matrix AI, which is convolution against PI. Somehow we think of these PIs as our colors in this setting. And then the first thing you prove is that the quantum automorphism group, which is somehow the colored quantum automorphism group, which is, the automorphisms that preserve the colors, which means that they have to commute with all of these matrices, that this is equal to the original quantum group gamma. So how does one prove that? I mean, you need to have an action that commutes with all of these adjacency matrices, right? So it means that it commutes with all the convolutions against PIs. But PIs, generate an infinity of gamma, or they can be even linearly, span an infinity gamma. You can do whatever you want there. So from this commutation, you would conclude that your action has to commute with all the left convolution operators, all of them. So basically, it has to be given by the right action. It has to factor for the right action. This is the only possibility, because you commute with everything acting from the left. So this is not very difficult. This is the proof dimension. Of course, you need to check some details, but I think you can. This is an idea that appears in many ways in many parts of mathematics. This is quite common. So what is the decoloring procedure? We have this projections pi, right? So it's a finite set of projections. So we look at these indices I, and they form some finite set which we call V, which will be the vertex set of some sort of classical graph. So we choose a new algebra, B, which is the function algebra of the finite quantum group that we had, and then we tensor it with some commutative CST algebra, right? Just functions on the vertex set V. So this is how we enlarge the algebra. And then on V, we define some nice classical graph, which somehow has almost all degrees of the vertices different. So this is, for a finite graph, it's not possible for all the degrees of the vertices to be different. Somehow two of them have to be the same. But you can construct examples that, besides that, almost all of the degrees are different. So I will explain soon why it's important. And then we can define the bigger quantum adjacency matrix on this tensor product, which will be you do identity tensor this A as the first part, and then you sum up all these AIs, right? So you combine all these quantum adjacency matrices AIs, and you tensor with PI, where PI is the projection onto the vertex I on the side of the functions on V. And then what we proved is that the quantum automorphism group of this A tilde is exactly the original finite quantum group gamma. So how do we do that? Basically, we use this degree matrix. So you look at the degree matrix of this A tilde, and then all these AIs, so all the convolution operators, they are regular quantum graphs. So it means that you apply AI to the unit, you get some multiple of the unit. It means that if you look at the the degree matrix of this A tilde, it means that on the left leg, the one coming from the quantum side somehow, you only get some numbers, and you only get non-trivial things on the other side. And then you look at the numbers. So then at each PI, so at each coordinate, you have some number, which is like the sum of the degree of AI and maybe a degree of A. And then you see that almost all of these numbers are different. So the degree matrix somehow has this form that you are given explicitly spectral decomposition. It has to commute with the actions. So all the spectral projections commute with the actions. And this way, apart from two of them, you can extract all these projections PI. And then if you know that you have these projections PI, then cutting by them, you can get back the AIs. And then there's some extra argument that even though you cannot somehow distinguish these two that have the same degree, you can somehow separate them by an extra argument. So it means that basically using this, you get that in the sum defining A tilde, all of these things, all of these AI tensor PI are separately intertwiners. And then it means that each AI is an intertwiner, basically, and then you use the colored version, right? Because if all the AIs are intertwiners, then you have to come from the right action. So it's really this decoloring procedure. So what I think is nice about this decoloring procedure is that it's actually, even for classical groups, it's more efficient than Frucht's construction. It's just, we just get a smaller graph. So basically it's because we had to work with quantum graphs. So by design, somehow our approach had to be more algebraic. We couldn't really do these geometric things of inserting subgraphs instead of edges, things like that. So we just had to, devise an algebraic formula, and turns out to be simpler than this typical classical construction. What is also nice is that if gamma is a classical group, we actually prove that I'm sorry, and also I should mention that if gamma is a classical group, then of course an infinity of gamma is commutative. So this tensor product is also commutative, right? So as a result, we get a classical graph. Right? So this is important to note, right? So if we start from classical group, the result is a classical graph with gamma as the automorphism group, and somehow it's more efficient than Frucht. But if you see here, I mean, we proved that the quantum automorphism group of this thing is gamma. So we actually constructed a classical graph whose quantum automorphism group is the original classical group gamma, right? So it's a graph which doesn't have non-trivial quantum automorphisms, right? And this is a quite recent result of Josef van Dobbe de Bruin, David Robertson, and Simon Schmidt. And then this I just leave as a question because we don't know how to solve it. Is that okay? In general, for quantum graphs, just like for quantum permutation group, in general, it's not a finite quantum group, right? It's a compact quantum group. It's infinite. So many quantum graphs, many finite quantum graphs, they can have infinite quantum automorphism groups, right? There can be some compact quantum matrix groups. And actually, we couldn't find a single example of a compact matrix quantum group that is not the quantum automorphism group of some quantum graph. I mean, I believe that some of them shouldn't be, but yeah, I don't know how to construct examples. Okay, and now I'll pass to this second question, right, of whether you can just already find the quantum Cayley graph such that you don't have to perform the decoloring procedure. And I will only focus on the co-commutative case, right? So our gammas will be duals of classical finite groups. But this is basically the only setup in which we have some answers. So in this setting, okay, we have the infinity of gamma will be just the classical complex group algebra of G. We take P to be some rank 1 projection. And then we have this easy criterion that if the Fourier transform of P, which is a function on G, separates points of G, then the quantum automorphism group of this group algebra with this quantum lattice matrix is equal to this gamma. So this sometimes happens. For example, if G admits a faithful irreducible representation, then a generic choice works. So you just basically choose a random rank 1 projection inside this subspace, and it works. So examples that appear here are, for example, permutation groups, dihedral groups, and things like that. There is, if I can recall correctly, there is a theorem characterizing which groups admit a faithful irreducible representation. So basically, so you can have the whole list. But what is nice, so for example, we get this dual of S3, right? So for duals of S3, we have this nice result. And as you recall, it's not even, this is one of the Banica and McCarthy's examples, right? So this is a thing that is not the quantum automorphism group of some classical graph. And then we have a more general result that for any non-abelian group, there exists a projection P in the group algebra such that the quantum automorphism group is the dual of G. So here a procedure is slightly more difficult. We need to look at somehow rank 1 projections in different representation spaces and somehow combine them nicely. But this is also a somehow genericity argument. So we prove that almost all choices work. Okay, and I think that's all I wanted to say today. So thank you very much for your attention.
Thank you. Question. Any question online or offline? I have several questions, but someone has a question. I can start. So you prove that any finite quantum group is a quantum automorphism group of a quantum graph. Can you expect to make new finite quantum group by considering some quantum graph and computing the quantum automorphism group? Can you expect to make something new like that?
Like that. I didn't think of it this way, but that's an interesting question. Yeah, this is something maybe because invisible you get all of them, right? In like that. So maybe that could be a way to produce something. Yeah, but of course for this you need a nice procedure for constructing some quantum graphs. And there's this issue like with quantum graphs, if you do like a generic choice, then of course it has no symmetry. So you have to be very precise with your construction. Yeah, but so I don't know. Maybe that would be very nice, but yeah, I don't know.
Okay, and so I guess the quantum automorphism group of a finite the quantum graph is not always a finite quantum group. I mean, if you
No.
Yeah, of course. So can we characterize which one provide a finite quantum group? Do you see some?
Like characterize which quantum graphs have finite quantum automorphism groups. Yeah, I don't know. I mean, I think even for classical graphs, it's not known. So it's already a difficult question for classical graphs, I would say. Of course, very nice question, very interesting, but probably very difficult. Because I think one should start with understanding the classical case even better. I think people are like the people that I mentioned is like Van Dobbe de Bruin, David Robertson, and Schmidt, and they have many very nice results about quantum automorphism groups of classical graphs. So they really so I think one should start there, trying to understand this question.
So actually, in the context of what just Palko asked, I think any quantum graph which have some sort of classical counterpart. I mean, because when there are classical counterparts, the free product picture of one gets into picture and makes the quantum group infinite dimensional. So maybe like starting with a direct sum of matrix algebras and putting the adjacency relations in such a way, such that it doesn't violate the orthogonality in the center of that algebra. Something like that. I mean, the vertex set has to have not just purely a matrix algebra, but the direct sum of something which has like a non-trivial center and all. And anything that acts on the center, it will give you a infinite dimensional object. From the Wang's point of view, the way Wang constructed the quantum permutation group and all, like in the context of like four sets.
Okay. So you mean that if you have a quantum matrix symmetry that somehow preserves the center, then you have a classical graph.
Yeah, something like that. Yeah, I mean that is not that will be something like a necessary condition, but not a sufficient one, I might add.
Okay. I see. Could be. Yeah, there are some ways to associate a classical graph to a quantum graph. I mean, maybe more in this operator system setting. So like there is a paper of Andrew Swift and Javier Alejandro Chavez Dominguez studying connectivity of quantum graphs, and they associated to for an operator system, they associate to each orthonormal basis of Cn a classical graph, somehow a classical version, somehow like localization to this orthonormal basis. So this is maybe another thing to look at.
Add something. So I actually had one thing to ask. I mean, the thing that we're taking when you are like taking the n times convolution.
I stopped hearing you. I don't hear you anymore.
Of generating projections. Why do you somehow? What I was just. I was. Can you hear me?
Yeah, now I can hear you. Yes.
Yeah. So what I was saying is that when you are like talking about this n times convolution product of generating projections,
So here, right?
Yeah. Why don't considering some sort of union of all paths inside quantum graph, something like that?
Why, you mean?
Yeah,
Yeah, so this,
because like in the context of the classical context, generating a one-dimensional generating projection is nothing but when you multiply a group element by another group element. So these
yeah,
rank one projections are somehow represented by a group element, and then you are like doing G into G square. So doing G square means you are taking P star P, something like that. So, I mean, whatever I'm
yes, so,
saying
yes,
may not have any meaning by that. I'm just asking.
yeah, so this is very, very similar. So this convolution somehow correspond to these things. So somehow, so P you should think as the whole set. You have some group elements, and then this convolution of n somehow will be taking all products of length n of these group elements.
Yeah, so G
Right,
power
so
n basically you are doing.
basically G power n, yeah, and of course because somehow some products can be the same, right? You're not in a free group, so some of them can be the same. That's why it's not necessarily a projection.
Yeah,
But that's why somehow you need to take the support. But yeah, this is exactly the idea.
Okay. So, thank you.
So I have some other question. If do you know the notion of fusion rings? Fusion ring, for example, the tensor product of
Yeah.
So I feel like you can make a quantum graph from a fusion ring.
Okay. Yes, possible. So maybe fusion ring. Yeah.
See the same.
Because
So what?
sorry, the quality is not great. Can you say it again?
So Jin Song said it is the same thing. Quantum graph and fusion ring.
Yes, the dual fusion actually is in our paper. The commutative part actually can be generate more.
So it's the dual of the fusion ring.
It should be the dual fusion.
Okay. So Jin Song said that the dual of the fusion ring should be a quantum graph.
In fact, it's not just fusion ring, it should be the dual fusion category because it has the category structure. It's not just an algebra structure. So it's not right to say it's just a fusion ring.
So you need fusion category.
So
yeah, otherwise
maybe yeah. So I don't know that much about it. So I know that there's some recent papers like by Mike Brown and Roberto Hernandez Palomares when they somehow developed this in the setting of C-star tensor categories. So this might be related, right? This is maybe somehow more rigid than fusion, I guess, but yeah, but it might be related, right? So they also have examples coming from subfactors, things like that.
Yeah, in fact, this was also my another question. There is in planar algebra theory, there is a theorem called the graph embedding theorem. So you have a subfactor and you have a principal graph, and they are able to make a planar algebra from this graph and to recover the subfactor. So maybe you are not familiar with this notion. So I wanted to ask if there is a relation between these two things.
Yeah, I don't know. Yeah, just I don't know.
The whole setting of this book is in a sub-framework. It's a subset of our framework. This is for sure.
Okay.
So you don't have to worry about that.
You don't have?
You don't have to worry about that. It is a special case.
Okay. Okay. Any other question online? So I guess I don't have any more question. So we can thank you again.
Yeah, thank you for having me.
Nice talk. Very beautiful results.
you.
So we'll stop the record.